All right, hello everyone, and welcome to my channel. This channel is for educational purposes, and we take a look at great theories of everything from the recent and ancient past, and go deep into them and try to flesh out, um, what they're talking about and how it can benefit your life. Your paradigm shifting and your holistic worldview. And today is our 479th video that we've done on Dewey B. Larson and his reciprocal system of theory. And Mr. Larson lived in the 20th century, and in 1959 he proposed his two fundamental postulates about how the universe operated, and that put him in kind of a rare class of scientists who attempted to construct their universe upon motion. Larson's first postulate says that the universe is composed entirely of motion, and motion for Larson was the relationship between space and time. And that is a reciprocal relationship between space and time. And that space and time, both space, time, and motion, the space and time do not have any independent existence. They only exist together in motion. And space, time, and motion come in 3 dimensions and in only discrete units. Now, I go into that quite a bit more in any of my 474 videos, the first 474 videos that I've done on this topic. So if you want any more of explanation, please check out one of those earlier videos. For now, we're going to get into kind of a later phase here where we're reading from one of Larson's books called Basic Properties of Matter. This book is on chemistry, and Larson uses his 2 fundamental postulates to deduce a theoretical universe, and then takes his theoretical universe and compares it with the measured universe of the legacy scientists that they've compiled in their, they went over in their laboratory experiments, and then they compiled in their scientific tables about the various basic properties of matter, the melting point and the compressibility and so on. This chapter here is on electric currents, and we are in our 3rd installment on this chapter. So rather than kind of rehashing the reciprocal system, I just want to get into reading directly from Larson, and I will try to explain anything that might not be related in one of my earlier videos. But Larson sometimes explains this stuff too. Okay. In a universe composed entirely of motion, an electric charge applied to a physical entity must necessarily be a motion. Thus, the problem faced in the theoretical investigation was not to answer the question, what is an electric charge, but merely to determine what kind of motion manifests itself as a charge. The identification of the charge as an added motion not only clarifies the relation between the charged electron that is observed experimentally and the uncharged electron that is known only as the moving entity in the electric current, but also explains the interchanges between the two that are the principal support for the currently popular opinion that only one entity, the charge, is involved. And just to refresh, in the last episode or the one before, Larson showed how the electron in its natural state is uncharged. That goes against legacy scientists who say that the electron is basically synonymous with the charge. Larson says that there's an uncharged electron, but that electron can be charged. And the uncharged electron is electric current, and the charged electron is, what you would call static electricity. It is, and so there is a motion between them. In order for the uncharged electron to acquire a charge, that's basically like saying that this uncharged electron acquires another motion. And the motion of the uncharged electron is that it is a rotating unit of space. Okay, so that is the electron. The uncharged electron is a rotating unit of space which travels through matter, because the relationship of space to time, matter made out of time primarily, the relationship of space to time is motion. And so a rotating unit of space is naturally going to move through matter. And depending on that matter is going to be the amount of resistance that it encounters, the temperature of that matter, and how much time and or space is in that matter. And so keeping that in mind, let's go from there. It is not always remembered that the opinion achieved general acceptance only after a long and spirited controversy. There are similarities between static and current phenomena, but there are also significant differences. Inasmuch as no theoretical explanation of either kind of electric effect was available at the time, the question to be decided was whether to regard the two as identical because of the similarities, or as disparate because of the differences. Once made, the decision in favor of identity has persisted, even though much evidence against its validity has accumulated in the meantime. The similarities are of two general types. Some of the properties of charged particles and electric currents are alike, and similarities are of two general types. One, some of the properties of charged electrons and electric currents are alike, and two, there are observable transitions from one to the other. Identification of the charged electron as an uncharged electron with an added motion explains both types of similarities. For instance, a demonstration that a rapidly moving charge has the same magnetic properties as an electric current was a major factor in the victory won by the proponents of the charge theory of the electric current many years ago. But our findings are that the moving entities are electrons or other carriers of the charges, and the existence or non-existence of electric charges is irrelevant. The second kind of evidence that has been interpreted as supporting the identity of the static and current electrons is the apparent continuity from the electron of current flow to the charged electron in such processes as electrolysis. Here, the explanation is that the electric charge is easily created and easily destroyed. As everyone knows, nothing more than a slight amount of friction is sufficient to generate an electric charge on many surfaces, such as those of present-day synthetic fabrics. It follows that whenever a concentration of energy exists in one of these forms that can be relieved by conversion to the other, the rotational vibration that constitutes a charge is either initiated or terminated in order to permit the type of electron motion that can take place in response to the effective force. It has been possible to follow the prevailing policy regarding the two different quantities as identical, and utilizing the same units for both only because the two different usages are entirely separate in most cases. Under these circumstances, no error is introduced into the calculations by using the same units, but a clearer distinction is necessary in any case where either calculation or theoretical consideration involves quantities of both kinds. As an analogy, we might assume that we are undertaking to set up a system of units in which to express the properties of water. Let us further assume that we fail to recognize that there is a difference between the properties of weight and volume, and consequently express both in cubic centimeters. Such a system is equivalent to using a weight unit of 1 gram, and as long as we deal separately with weight and volume in each in its own context, the fact that the expression cubic centimeter has two entirely different meanings will not result in any difficulties. However, if we have occasion to deal with both quantities simultaneously, it is essential to recognize the difference between the two. Dividing cubic centimeters of weight by cubic centimeters of volume does not result in a pure number, as the calculations seem to indicate. The quotient is a physical quantity with the dimensions of weight over volume. Similarly, we may use the same units for electric charge and electric quantity as long as they are employed independently and in the right context. But whenever the two enter into the same calculation or are employed individually with the wrong physical dimensions, there is confusion. This dimensional confusion resulting from the lack of distinction between the charged and uncharged electrons has been a source of considerable concern and some embarrassment to the theoretical physicists. One of its major effects has been to prevent setting up any comprehensive systematic relationship between the dimensions of physical quantities. The failure to find a basis for such a relationship is a clear indication that something is wrong in the dimensional assignments. But instead of recognizing this fact, the current reaction is to sweep the problem under the rug by pretending that it does not exist. As one observer sees the picture, quote, "In the past, the subject of dimensions has been quite controversial. For years, unsuccessful attempts were made to find ultimate rational quantities in terms of which to express all dimensional formulas. It is now universally agreed that there is no one absolute set of dimensional formulas." End quote. This is a very common reaction to long years of frustration, one that we encountered frequently in our examination of the subject treated in Volume 1. When the most strenuous efforts by generation after generation of investigators fail to reach a defined objective, there is always a strong temptation to take the stand that the objective is inherently unattainable. Quote, "In short," says Alfred Land, "if you cannot clarify a problematic situation, declare it to be fundamental." end quote, or no, fundamental, uh, and then proclaim a corresponding principle. So physical science fills up with principles of impedance rather than explanations. In the universe of motion, the dimensions of all quantities of all kinds can be expressed in terms of space and time only. The space-time dimensions of the basic mechanical quantities were identified in Volume 1. In this chapter, we have added those of the quantities involved in the flow of electric current. The chapters that follow will complete this task by identifying the space-time dimensions of the electric and magnetic quantities that make their appearance in the phenomena due to charges of one kind or another and in the magnetic effects of electric currents. This clarification of the dimensional relations is accompanied by a determination of the natural unit magnitudes of the various physical quantities. The system of units commonly utilized in dealing with electric currents was developed independently of the mechanical units on an arbitrary basis. In order to ascertain the relation between the arbitrary system and the natural system of units, it is necessary to measure some one physical quantity whose magnitude can be identified in the natural system, as was done in the previous determination of the relations between the natural and conventional units of space, time, and mass. For this purpose, we will use the Faraday constant, the observed relation between the quantity of electricity and the mass involved in electrolytic action. Multiplying this constant, 2.89366 times 10 to the 14th electron space units, or ESU over G equivalent, by the natural unit of atomic weight, which is 1.6579 times 10 to the minus 24th grams, which is just the reciprocal of the Avogadro's number, we arrive at 4.80287 times 10 to the minus 10 ESU as the natural unit of electric quantity. The magnitude of the electric current is the number of electrons per unit of time. That is, units of space per unit of time. Remembering that electric current, an electron is a rotating unit of space. That is, units of space per units of time, or speed. Thus, the natural unit of current could be expressed as the natural unit of speed, which is the speed of light, 2.99793 times 10 to the 10th centimeters per second. In electrical terms, it is the natural unit of quantity divided by the natural unit of time, and amounts to 3.15842 times 10 to the 6th ESU per second, or 1.05353 times 10 to the minus 3 amperes. The conventional unit of electrical energy, the watt-hour, is equal to 3.6 times 10 to the 10 ergs. The natural unit of energy, 1.49275 times 10 to the minus 3 ergs, is therefore equivalent to 4.14375 times 10 to the minus 14 watt-hours. Dividing this unit by the natural unit of time, we obtain the natural unit of power, which is 9.0899 times 10 to the 12th ergs per second, which equals 9.9 9.6099 times 10 to the fifth watts. A division by the natural unit of current then gives us the natural unit of electromotive force, or voltage. 9.31146 times 10 to the 8 volts. Another division by current brings us to the natural unit of resistance. 8.83834 times 10 to the 11th ohms. The basic quantities of current, electricity, and their natural units in electrical terms can be summarized as follows. Okay, so here in this table, he's providing not only the numbers, but also the space-time signature for each one of the units, because that's what we're dealing with when we're dealing with the universe of motion, is all forms of motion are relationships between space and time. So all forms of motion, which include all of our scientific phenomena, all of our units, such as mass and energy and force and acceleration and current and voltage and so on, they are all fractions, with space or time as the numerator and time or space as the denominator. So here we have the space quantity, which is the basically a number of electrons. So space or quantity 4.80287 times 10 to the minus 10 ESU. So that's the natural unit of quantity. Current, which is space over time, or otherwise known as speed. And that is 1.05353 times 10 to the minus 3 amperes. The natural unit of power is 1 over S. For 9.8099 times 10 to the fifth watts. The natural unit of energy, time over space, 4.14375 times 10 to the minus 14th watt hours. Voltage, which is time over space squared, which is 9.31146 times 10 to the 8th volts. And then resistance, which is time to the second power over space to the third power. And that is 8.836 or 8.83834 times 10 to the 11th ohms. Another electrical quantity that should be mentioned because of the key role that it plays in present-day mathematical treatment of magnetism is current density, which is defined as the quantity of charge passing per second through unit area of a plane normal to the line of flow. This is a strange quantity, quite unlike any physical quantity that has previously been discussed in the pages of this and the preceding volume, in that it is not a relation between space and time. When we recognize that the quantity is actually current per unit of area rather than charge, a fact that is verified by the units amperes per square meter in which it is expressed, its space-time dimensions are seen to be space over time times 1 over space to the second power, which is, current over area. And so those work out to be 1 over space time. So that is not a kind of motion, because it is not a relationship between space and time. It is space and time in the same on the same side of the divisor there. These are not the dimensions of a motion in a property of motion, or a property of motion. It follows that this quantity as a whole has no physical significance. It is merely a mathematical convenience. The fundamental laws of current electricity known to present-day science, such as Ohm's law, Kirchhoff's laws, and their derivatives, are empirical generalizations, and their application is not affected by the clarification of the essential nature of the electric current. The substance of these laws and the relevant details are adequately covered in existing scientific and technical literature. In conformity with the general plan of this work, as set forth earlier, these subjects will not be included in our presentation. This is an appropriate time to make some comments about the concept of natural units. There is no ambiguity in this concept so far as the basic units of motion are concerned. The same is true in general of the units of the simple scalar quantities, although some questions do arise. For example, the unit of space in the region inside unit distance, the time region, as we are calling it. Again, because of the discrete unit postulate, space and time have to come in full units. And so when two atoms or particles or molecules approach each other to 1 unit of distance, which is approximately 2 millionths of an inch, then they can no longer get any closer because they're already 1 unit apart, and they can't get any less than that because there is no such thing as less than 1 unit of space. So what they do instead is they move outward in time, which by the reciprocal postulate, space and time being reciprocals of one another, is equivalent to moving inward in space. And so it appears to us as they are continuing to move inward in space. Larson calls that equivalent space, is the spatial equivalent of time. The action is really occurring in time, but we see it in space because we are anchored to a spatial reference system by gravity. And so we can't see time, we only see space. But when we look into equivalent time, we see, and into the time region, we see it in kind of a distorted picture. And he's going to explain at least part of that here, the interregional ratio. Okay, so there is no ambiguity in the concept. For example, the unit of space in the region inside unit distance, the time region as we are calling it, is inherently just as large as the unit of space in the region outside unit distance. But as measured, it is reduced by the interregional ratio, which is 156.444, which is basically the 128 times 11 over 9. And I've done an article, a video about the article where he explains how to derive that. So if you're wondering, just look into my playlist and look for the interregional ratio. For reasons previously explained, we cannot legitimately regard this quantity as something less than a full unit, since, as we saw in Volume 1, it has the same status in the time region that the full-sized natural unit of space has in the region outside unit distance. The logical way of handling this situation appears to be to take the stand that there are two different natural units of distance of one-dimensional space, a simple unit and a compound unit that apply under different circumstances. The more complex physical quantities are subject to still more variability in the unit magnitudes, because these quantities are combinations of the simpler quantities, and the combination may take place in different ways under different conditions. For instance, as we saw in our examination of the units of mass in Volume 1, there are several different combinations of natural units, and therefore, I might have skipped a line here. For instance, as we saw in our examination of the units of mass in Volume 1, there are several different manifestations of mass, each of which involves a different combination of natural units, and therefore has a natural unit of its own. In this case, the primary cause of variability is the existence of a secondary mass component that is related to the primary mass by the interregional ratio, or a modification thereof. But some additional factors introduce further variability, as indicated in the earlier discussion. Okay, that is the end of Chapter 9 on electric currents. Chapter 10 is called Electrical Resistance, and we will start up with that chapter beginning tomorrow. So thanks for tuning in today, and have a wonderful day.